I narrowed down the title a little bit because the history of accelerators and of accelerated particles is as long as mankind. You know, from facing the big problem of a mammoth to trebucheting the city wall around medieval cities, accelerated particles have been important throughout of all mankind. So I'll only talk about more modern particle accelerators. The largest one ever endeavored to be built is this one, the superconducting supercollider, 80 kilometers long. This is Dallas, right next to Dallas, as large as Dallas, as if it was a city wall. Unfortunately, rest in peace, this project started, spent already $2 billion, but then it was terminated in the Clinton administration. But still, that's the largest accelerator ever endeavored to be built, 3 times the energy even of the LHC, which is currently the largest accelerator with 27 kilometers. The ethos of being an accelerator physicist is staying the same. We are still facing the largest scientific problems. And as the city wall defined medieval cities, their importance and their strength, so now it's the science project and technology that defines the importance and influence of cities, countries, and cultures. So particle accelerators are at the very forefront of that, so you can take some pride in being an accelerator physicist. Particle accelerators are not all that large, of course. So small ones, electron microscopes, and large ones like the LHC, all have very basic principles that are similar. Of course, they have a source, they have charged particles, they have focusing elements, they steer the beam. That's true from the very small to the very large. Also important is that all of these accelerators have many subcomponents. For example, the LHC itself is a large stage of a large accelerator with many initial accelerators. Something like 7 accelerators have to be passed through to get a beam to the LHC. That's a feature of all large accelerators. And as you know, accelerators have had large influence in our culture, from industrial accelerators to medical accelerators to accelerators in research. So arguably, since 43, every 3 years there has been a Nobel Prize has come with data from accelerators. So accelerators are really extremely dominant in industry as well as in science. So let's go through a bit of the early history, how charged particle accelerators came about. At the very beginning, you could argue Clerk Maxwell invented electromagnetism. And of course, electric fields are essential for accelerating charged particles. Hertz, nearly a generation later, discovered that the electromagnetic waves that Maxwell described in his theory are actually what makes up light. So that was, of course, so important for the insight in nature. Then positively charged particles get discovered. Leonard was the first to extract cathode rays, meaning electrons, out of a vacuum system into detectors. That was kind of important, but it's just a very thin aluminum foil. I think it's one of the least deserved Nobel Prizes, or maybe the easiest one Nobel Prizes. He got a Nobel Prize for his Leonard window of just a thin aluminum sheet. The next least deserved Nobel Prize is in an automatic operating charging light on a buoy, which I think went to a Swedish scientist, because there were so many discoveries from my interpretation. Anyway, so that is the Leonard window. It's still used today. Next important thing is that J.J. Thomson discovered that these cathode rays are actual particles. We call them electrons. And he found that because they follow the Lorentz force equation for charged particles. Then George Thomson, his son, discovered that no, electrons are actually waves. So it stayed, this controversy of particles against waves stayed in the same family. Interesting is also that J.J. Thomson was at Cornell for nearly 2 years, and some of the initial discoveries or the initial indications of electrons being waves by interference patterns came from experiments that he made at Cornell. And here are some of the fringes that you get when you send cathode rays through a foil. You get interference patterns because electrons are very used. And then, of course, after leaving Cornell, he received a Nobel Prize. Then you all know the Rutherford experiment. Rutherford took accelerated particles from natural decay, so he got alpha particles from alpha decay. They can have a lot of energy. Here he used 7.7 MeV. No accelerator needed, and that's what led to the discovery of atoms having a dense core. You all know this experiment. Rutherford also used natural alpha particles to actually induce the first artificial nuclear reaction. That's super important. And then he and others thought if we had such high energy particles that we can artificially produce, we could start a whole new field of physics of these artificial nuclear reactions. So in 27, he said to the Royal Society, if it were possible in the laboratory to have a supply of electrons and atomic matter in general, of which the individual energy in motion is greater even than a few MeV of alpha particles, this would open up an extraordinary new field of investigation. So nuclear physics, high energy physics, that's all what he envisioned. Some people say he gave up because he could only produce some 100K EV, but that's actually not true. In this speech to the Royal Society, he said, I see no reason why this technology should not be possible to be developed. In the next year already, actually, Gamow found the tunneling effect. The tunneling effect is an effect that that explains the lifetime of alpha decay. So alpha decay you can model as alpha particles bouncing back and forth in an atomic nucleus. And the bounce, depending on how large the nucleus is, they bounce back and forth with a certain period. And they have a chance of tunneling through the Coulomb expansion potential. You can calculate the tunneling likelihood. From that, you can calculate the lifetime as a function of the energy. Is this zero energy? Of course, the kinetic energy with which the alpha particles come out corresponds to the bouncing energy they have in the nucleus. So the energy with which they come out should be correlated with the lifetime. Because if you tunnel through a bigger potential barrier, the lifetime will go down. It's longer. It takes longer to get out. So this strict correlation between lifetime and energy was compared to data already in 28, and you get a nice line from 10 to the minus 6 seconds to 10 to the 17 seconds. It's a simple physics law that works over the largest number of days, largest order of magnitude. So it was an extremely important breakthrough to justify quantum mechanics tunneling effects being real. And if that's possible, we might not need as much energy to get into the nucleus to induce nuclear reactions. And people realized, even though the alpha decay, to induce nuclear reactions by alpha particles, we needed about 10 MeV, much less energy might be possible to induce nuclear decays because we can tunnel into the nucleus. And that's why the first nuclear reactions then were done with only about 400 to 700 K, much below the Coulomb potential. Good, so that was the start of lower energy accelerators, and then the field of accelerated physics started to become more advanced. One interesting one is this here. So in the Swiss Alps, a team of Brush and Lange and Orban put two spheres over a valley. The charges in the sky charged up the spheres, and you get a lot of voltage. Unfortunately, one of the researchers, Orban, got electrocuted, so that was a kind of a dead end in accelerator technology. My presentation is a little bit Cornell-centric. I just here go quickly through the timeline of accelerators at Cornell, and then I want to use this talk not only to go through timeline of accelerator developments, but also to drop names of accelerators so you learn what accelerator names mean, what the accelerators are available. The first cyclotrons were built in Berkeley in '92. Shortly later, Livingston came from Berkeley, built the first non-Berkeley cyclotron here at Cornell. It was just in the neighboring building in the basement. There's only a plate left because the cyclotron was in the late 50s donated to Jerusalem University, where it continued to do research. Here it did research for such a long time that Bob Wilson, who was the director here, said this cyclotron produced more PhD theses than protons. Then in '49, the first, so after the Second World War, shortly after, the first synchrotron that stored beam was here at Cornell. In '54, the first synchrotron with strong focusing was built. Strong focusing means focusing by quadrupoles. is used in every large accelerator today. It's the basic focusing principle everywhere. The first accelerator was right here in the neighboring building. Then the Caesar accelerator that's still operating today was built on the Cornell campus and had high energy physics, and then the first multi-turn energy incubator that you can still build here as well. So these are two accelerators. Here's a quick timeline. So this is the first cyclotron that was built here, with Daniel was the second lab director here, all the way up to Caesar and CBA. So welcome at Cornell. Thanks for visiting our accelerators. And I hope you enjoy your time and you learn a lot. So this is a map of the campus. Wilson lab that you see is here, and the Caesar accelerator end of the year one goes completely through the field that you see in front of the campus. So at the moment there's construction, so it looks better. The tunnel, so this picture shows you how old this accelerator was. Very rudimentary tunnel machine, started in '65 to dig around this 800-meter tunnel. And Bob Wilson was the person who built the tunnel. If you go to some sightseeing, Ithaca Falls, there's a tunnel going through the hill. This is the entry. Now there is so this is after a gate, there's actually a big metal gate, so crawling in is pretty complicated, and we don't encourage you to do it. But this tunnel still exists. It was the first tunnel that Ezra Cornell built before he founded the university. Now back to accelerators. There are three main accelerator techniques: direct voltage accelerators, just a DC field that accelerates charged particles, of course. The resonant accelerators, like SIF accelerators that some of you work with electric fields and so forth. And transformer accelerators, where you basically have a transformer, like your wall plug transformer, where the secondary coil in the transformer is the particle. Three types of accelerators, let's go through those. The Van der Graaf accelerators is one of the earliest ones. As you see, these early techniques come from the 30s. This is basically the accelerating type that you know from high school when you rub a cat fur on a plastic stick. The stick gets charged up a sphere multiple times, and the voltage can get quite high. So that's just made more systematic by a conveyor belt that's non-conducting, a comb that combs charges onto this conveyor belt, and the charges go up and charges here. There are several names for these kind of Van der Graaf accelerators, depending on what is used as a conveyor belt. But they are all Van der Graafs and go to just a few MeV before embracing produce lightning and discharge the charged sphere. Here's an example, and indeed it really looks like a comb. Here's the comb, here's the non-conducting conveyor belt. That's called a Van der Graaf. Often you hear something like a pelletron. Same principle, except the conveyor belt has individual charges that are not conductively connected, so you don't get a current down these pellets. And the conveyor belt then transports charges with this chain up to the charge sphere. I'm mentioning this because there's an important accelerator at Fermilab that uses a pelletron to produce electron beams to cool antiprotons. Protons are still used at Fermilab. So that's why the name pelletron comes up sometimes. Van der Graaf accelerators are also used for so-called tandem accelerators. When you hear that name, it just means that you have a Van der Graaf that accelerates a negative beam to some high potential. There, the negative beam hits a target, loses its electrons. Now it's positively charged and gets pushed away from the target back to ground potential, so you gain energy twice. That's why it's called a tandem Van der Graaf. Brookhaven National Lab, for example, still uses a tandem Van der Graaf for some of the ion species that are sent into the ring collider. Those of you who know Dasbury is an English laboratory that runs the Cockcroft Institute, which is the student institute that's most similar to CBB. And if you go to Dasbury, you see this thing that looks like a water tower. But that's actually the tower that runs a tandem Van der Graaf. And yes, that is no longer in operation, but in the hall below, one of the first energy recovery limits was built. And of course, at Cornell, we have C beta energy recovery limit. Next important, also from the 30s, is the Cockcroft-Walton accelerators. They are still around. You need you use diodes and capacitors. You have an RF voltage that successively charges up one capacitor after the other. They cannot discharge because of the diodes. So you get this ladder of capacitors charged up successively, and you get hundreds of capacitors that then operate many hundreds of kilovolts. These things get very large. For example, so this is about a little more than a meter. So these structures can get very high and complex, just to get a little bit more than a meter. Another accelerator that uses capacitors is quite interesting, and is still in use today. It's the max generator, again, from the early 30s. The max generator just uses a direct voltage to, in parallel, charge up hundreds of capacitors. And then you have spark gaps, which you fire very quickly, so that now the capacitors are in series. So the spark gap has a resistance much less than these resistors, so they act in series, and very suddenly you have the sum of all the voltages on these capacitors only for a very short time, so you get a huge current spike, and that's, for example, used to fire plasmas. You take a wire into which you shoot for very quickly this intense current pulse. It turns out that if you have two wires with the same current in parallel, the magnetic field of these wires makes them attract. So therefore, you get a pinch effect. The large current through that wire makes the wire contract. So you give a lot of current in a contracting wire, the wire explodes in the plasma. That's the max generator. Good, so now let's move on to resonant accelerators. Resonant accelerators, for example, like the cyclotron, have beams that go in circles, and while the particle goes in circles, these C's change just in the right rhythm their polarity from plus to minus, minus to plus, so that whenever the particle goes around, it gets accelerated, polarity changed, gets accelerated again, gets accelerated again. The cyclotron, as I said, so first cyclotron in 32 came from Berkeley, and Lawrence got his Nobel Prize for it. Livingston, who worked with Lawrence, then, as I said, came to Cornell and used the first non-Berkeley cyclotron here. Again, the accelerating voltages are not enormous, so Lawrence went to 1.2 MeV approximately, but was enough to induce nuclear reactions because of the sunning effect, so it became very important in nuclear physics. You cannot go to higher energy with cyclotrons because of non-relativistic motion, because of relativistic motion. If you get too high energies, then the speed of the particle doesn't increase much anymore with more energy, which means the speed of the particle gets out of sync with the changing electromagnetic field. The particle is just not getting fast enough to come around fast enough on the increasing radius of the orb. So it goes out of sync with the changing frequency in these C structures. You could compensate by that by making the magnetic field stronger to the outside. That would make the circles smaller on the outside so that the synchronization still works. The problem is only if you make the field stronger to the outside, here you go around, you make the pole shoes closer together, field stronger to the outside, that would produce a vertical defocusing of the beam. The field structure, because of the field bending over, makes the beam defocus vertically. So if you try to build a cyclotron that compensates by stronger fields to the outside, the relativistic effect, the beam would just explode vertically. That didn't work. It was, of course, tried. Didn't work. But there's an effect that you can use to compensate this vertical defocusing, and that's edge focus. If you have a dipole magnet that bends over the beam, but you don't send the beam perpendicular to the entry of the magnet, but you bend the entry face over somewhat, then you get a horizontal field component, right? The field bulges out of the top of the magnet and connects back to the bottom of the magnet. So this field that you see when you go vertically off the center plane produce a horizontal field component which can focus the beam. So the edge focusing can be used to focus the beam to compensate the vertical defocusing. And that's why modern cyclotrons look like this. If you look into a modern cyclotron, it has these very nice kind of clover leaf structures so that the beam, while it goes around, sees the edge angles just suitably every time it goes around so that the edge angle focuses the beam, so that the vertical defocusing that comes from making the field stronger on the outside is compensated. So now the field does get stronger to the outside to compensate the relativistic. Good, so then cyclotrons go to several MeV. The strong thing about cyclotrons is that now the particles stay in sync from the beginning to the end, often to something like 300 turns. But since particle is in sync in every turn, you can at every turn have particles. So particles can go around simultaneously in 300 different modes. So you have 300 bunches of particles going around simultaneously. You can produce continuous beams.
So what's the scale here?
So this is from Michigan, actually, one of the cyclotrons in Michigan. The scale is about, the radius probably like 90 centimeters or so. The largest cyclotron, I think, is at the PSI in Switzerland, where the diameter is probably something like 4.5 meters. So cyclotrons then early on were already used for cancer therapy. Cancer therapy, medical accelerators, of course, are very important still today. So people tried that out. They just took, they swallowed radioactive material to realize, oh, look at this. The radioactive material can be checked in a Geiger counter. That wasn't very healthy. So that was good to study charged particles and accelerators. That wasn't very healthy, so people got cancer, so they were put in the accelerator and were in therapy, and that of course wasn't very healthy either, so they went back to the accelerator. So there's some infinite loop. But just kidding aside, that was the first effort of doing cancer therapy in particle accelerators, and that's of course a booming field today. One of the best known cancer therapy machines in California, it's all because it was one of the earliest. It's called Loma Linda, so it has a source, first accelerator, synchrotron, so a ring accelerator, and then it goes into gantries that feed the beam to patients. They look so complicated because you want to irradiate the patient from different directions in order not to damage the path where the particle goes into the patient. So you need to rotate the beam around the patient. That's a pretty complicated arrangement. You say, well, it seems easier to keep that fixed and rotate the patient. The problem is that if you rotate the patients, the organs actually move around in major ways. So you can't keep the organs fixed. Bob Wilson, our first major lab director, actually was officially the second director, first one stayed only for 1 year. He gave the name to Wilson Lab, and then later he started Fermi Lab. That's why there's a Wilson Hall. So this Wilson became one of the major advisors of this Loma Linda accelerator. Had a lot of influence there, also because he wrote the first therapy paper for proton therapy. The next accelerator I want to mention is the microtron. It's basically like a cyclotron, except for electrons. So I told you cyclotrons are no good for relativistic particles because you need to increase the field too much to the outside. So for electrons, cyclotrons are no good at all, but microtrons are a little bit like that. You build a LINAC and send electrons around, and every time the electron goes around, it gains more energy, and you just make the energy every time increase sufficiently and make the path longer sufficiently so that every time the electron beam skips 1 RF wavelength. As the path gets longer, just make sure every time the electron skips 1 RF wavelength that you can have all electrons accelerate simultaneously. It's like the micron is like the corresponding thing to a cyclotron, but for electrons. And these exist, and the highest energy of this goes to about a GeV for electrons. So it's in the basement of a university lab in Germany, a very efficient way of accelerating electrons for nuclear. Okay, so cyclotrons, these microtrons could in principle, like a cyclotron, be circular, but you need an RF cavity inside so you can skip RF wavelengths. Another name that I want to drop is the Rhodotron, just because you can actually order it online. There are companies offering rototrons because they are pretty simple. So here you have a coaxial cable, basically. So inner conductor, outer conductor, coaxial cable, into which you put an RF frequency, so the RF voltage oscillates. In a coax cable, you have electric field from the inside to the outside. So the electric field from the inside to the outside oscillates going in, out. And you send from a source a beam in. From a source, you send beam in when the field is accelerating here. There's no field inside, so you travel inside without field until the field has reversed its polarity, so you get accelerated again. The dipole magnet sends you back, and you get accelerated, 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 accelerated. And here you get accelerated 10 times the energy and can go. So it's like going through 10 cavities at a time, even so you have only one little cavity. That's a rototron if you ever see it. Now, the Biederow linear accelerator is a concept that is still mentioned today. Biederow is this guy. Rolf Biederow, he was from Norway. He received his PhD for building the first linear accelerator, still named after him. The idea came from another Norwegian guy, Gustav Ising, who published it in 24, didn't build it though. Lawrence said of Ising because he suggested that he is the father of multiple acceleration, my meaning RF acceleration, oscillating frequency acceleration. So that's interesting. Remember Biederow, his name will come up again. So as a PhD project, he built the first type of a very influential accelerator. So if you have a PhD, better build a new technology of new acceleration. You'll get famous. But there's even better to come, so remember his name. Good. So in accelerators nowadays, we use RF cavities where we can have one RF source, have resonant excitation in many cells of cavities. As the particle goes through, when the field goes forward, field changes sign, and so on. And in every cell, the field changes sign, the particle can be accelerated continuously. It's called the traveling wave or standing wave accelerator. You know these beams in cavities because if you do RF research, the first of the type came from 1933. All this happens in the early 30s. The Alvarez linear accelerator is also a name that is often used today, so remember that. Here, you see you have these many cavities, where every time you go through a cavity cell, the direction of the acceleration changes. For example, here you go from minus to plus, but when you arrive in the next cavity, the field has changed from plus to minus, so you get accelerated here, accelerated here, accelerated here. Every cell you get accelerated because in the right rhythm, the polarity changes. But if you look at that, you can imagine that in the cavities where the electric currents oscillate back and forth, in this cavity wall, there's a current going in and the current going out. So actually, you don't need that wall. The Alvarez accelerator gets rid of these walls, has one large tank, has these shift tubes, and one large tank supplied by an RF field produces basically the equivalent of many cells. Alvarez also got a Nobel Prize, worked at Berkeley, and this is therefore named after him. Alvarez is pretty important in other fields because he realized that in the cyclotron at Berkeley, you can do very accurate isotope detection. You can take a nucleus with a certain charge, but depending on how many neutrons it has different radius, so you can figure out not only what particle type you have by the charge, you can also figure out which isotope it is, how many neutrons it has. And his son was a geologist and explained to his father that there is a boundary from about 65 million years ago that looks somewhat surprising. It's all over the world. It's this little boundary between rock formations 5 million years ago. So they identified with the cyclotron at Berkeley that this material comes from an asteroid and put therefore up the theory that dinosaurs were killed by an asteroid. So it was an accelerator physicist with a Nobel Prize who helped with his son, the geologist, to show that dinosaurs were killed by an asteroid. And that's the justified theory today. So everybody believes, every scientist believes that. Phase focusing became very important in RF acceleration. Turns out that if this is the time sequence of an RF wave in which you accelerate, you can only focus the beam in accelerate and focus the beam 1/4 of this acceleration. So it send the beam in just at the right time. That became very important. I mentioned that because it's associated with Macmillan in the US, this phase focusing. Macmillan was also in Berkeley, built the second synchrotron, second RF ring accelerator that stored the beam successfully. As I said, first was in Cornell. So Wilson at Cornell built the synchrotron, and he managed by field shimming, so putting little iron plates into magnetic fields to make sure the field is just correct, to keep the beam in a circle. He told that to his colleague Macmillan at Berkeley. Macmillan managed to store his beam and was the first to get nuclear physics results from it. So while we stored the first beam, they got the first science results. The reason I bring that up is because it's one of the many cases where independently a physicist in the USSR developed the same technology. And that is something you will experience in accelerator physics all the time when you say, oh, this comes from this certain physicist, and there will be some Russian in the room who says, oh, no, some Russian invented it. And usually another interesting thing is that Alvarez and Macmillan, who I just mentioned, with Lawrence, who also just mentioned, built the only company owned by 3 Nobel laureates, and it was a company developing color TV. Also, color TV is a tiny accelerator. So they didn't get much money from it, unfortunately, because their technology was not utilized in the first color TVs, which were built by Sony and had a slightly different technology. But at the end, commercially, that technology was a dead end, and the Nobel Prize technology became the basic technology actually used for color TVs from the 70s to the 90s. There's an excellent article in Physics Today that you should check out about this Nobel Prize company. Okay, important is radio frequency quadrupoles. I told you Cockcroft-Walton accelerators get really large to get a few MeV. And RFQ, and that was definitely invented only by Russians, is much smaller, gets the same energy by just having quadrupoles that having 4 rods that change their RF, change their polarity regularly by RF voltage. And they are shaped going inside and outside, so that get longitudinal field components that accelerate the beam. Works excellently, focuses this beam as well as accelerating the beam, and every large ion accelerator today has that as the first stage of acceleration. Third type of acceleration that I want to mention is transformer acceleration. So it's pretty simple. It's just a primary coil, like when you put a transformer into the outlet, primary coil that has an oscillating current, produces oscillating electric field. Here is the secondary coil that you would put into your laptop. But the secondary coil is an electron beam in a vacuum. That is called the betatron. You can still buy betatrons. They are used for electrons. They have been important also since the 30s. But here, the person who invented the betatron was 20 years old. It was Ralph Wiederer who built the first Linux. So if, my experience is if you get older, you don't feel so much older, but everybody else feels much younger. So if you are 21 already and you haven't invented a major technology for acceleration, you can look up to Ralph Wiederer. Now, synchrotrons are very common for large accelerators, and they are just an assembly of bending magnets and focusing quadrupoles. So it's called alternating focusing with quadrupoles, focusing quadrupole, defocusing quadrupole, and the beam bends around. So all large accelerators today are such synchrotrons. As I said, Vex and Macmillan in the space focusing, that was important to know exactly at what time one needs to inject beam into the synchrotron. Keep it stable. The first synchrotron was then built in 46, betatron magnet, first stored and built in a synchrotron at Cornell, and then first data taken by Macmillan in Berkeley. Wilson, I mentioned to you several times because he wrote the first paper on proton therapy. He was advisor at Loma Linda Therapy Center. He gave the name to Wilson Lab. He founded Fermilab. This is his face. He was also an artist and an architect. For example, the visitor center at the entry was his last architectural feat. Wilson designed that. Wilson Hall, designed by Wilson himself. That's the main building at Fermilab. Inside is amazing. And the first person he hired at Fermilab was an artist with whom he had worked here in Cornell, Angela Gonzalez. So she worked with him here at Cornell, and there's actually an artwork on the third floor in Wilson. If you get there, there's a meeting room. On the wall is kind of a colorful panel. It's an artwork from her. You can check it out. She has a website, or her daughter has a website of all her artwork, and that artwork has a photograph there and says location unknown. So if you want to see that lost artwork, see. So we notified her that this artwork is actually there, but we had no reply so far. There are many other artworks that come from Wilson. For example, if you go into the west entry, there is something that looks not symmetric if you look from the side, but if you look from below, it looks exactly like a Mercedes star, totally symmetric. It's the broken system, and many other very, very nice artworks from Wilson. For example, the power lines and the shape of a pipe. It's kind of cool. Now, Wilson Lab, or Wilson, also connects us to astrophysics, because there is this fancy building, which used to be a party hall of the only secret society at Cornell. There's a secret society at Cornell, and we call this building the Mausoleum. And it was built by the Sphinx Head Society, so every graduating class has a selection of very few, like 4 students, entering this secret society. So it's secret, so we don't know what they do, what they used to do in there, what they do today. But they were influential. For example, they invented Dragon Day, an important commotion at Cornell every year. They invented the name Big Red for our sports teams, and also they invented Slope Day, which is the end of the semester every year. And why do I mention Wilson? Because Wilson purchased that studio, that space as an art studio. He then sold it to Carl Sagan from Cosmos fame. And Carl Sagan's widow, Anduran, who actually wrote the text to Cosmos and its TV show, she sold it just last year to a millionaire who made his money from scrap metal all along the East Coast. And he has it currently being renovated by Pei Architects. Pei Architects is the firm of the sons of I.M. Pei. I.M. Pei is the most famous modern museum building architect in the world. He's dead by now, but he built, for example, the pyramids at the Louvre. He built famous art museums, for example, in Syracuse, in Bloomington, Indiana. The 20th Century Art Museum on the Washington Mall comes from him. Most famous architect for museums, and Cornell's Art Museum is the first museum he built. So make sure you visit Cornell's Art Museum, and that's encouragement. Any questions?
The RFQ, our particle, you had said something is usually the first acceleration stage in some systems.
Yes, ions. So ions and protons, usually they have a source, and you come out of that source with a few 10, maybe 100 keV, or a few hundred keV. And that's just DC acceleration. There's a DC electric field, come out pretty, I mean, for ions or protons, that's pretty slow. And then the next accelerator is an RFQ that gets you to decent acceleration. Typically, RFQs, for some historical reasons, are normalized to 750 keV. So you come out 750 keV or 1.5 MeV by 1 or 2 RFQs.
There's usually only 1 or 2? They don't
and no, they don't, because the gradient is not very large. So so they do 2 things, 3 things. They focus the beam because there's a quadrupole, they accelerate the beam, and they punch them. So you send a DC beam in it, so you have a plasma basically, where you produce protons or ions. You have a DC field, they come out of a little hole, but drift continuously out, and the RFQ bunches them into little buckets. And then once you have formed the buckets, you can now go into more efficient accelerators like it.
I see. Okay. That's new to me, thank you.
Okay, any other questions? So, as you heard in the presentation outside, the best way of learning is to ask questions in talks. So ask questions.
Is C beta a betatron, or is the beta like?
C beta is the Cornell, Brookhaven, ERL, Energy Recovery Linux test system.
Okay, so what type is that?
It's a Linux.
Okay.
Let's see. Thanks for asking. So let's see, one can probably not see it here. The picture I put in is too small, probably. Yeah, you can't really see. So what happens is you have a electron source, you produce very small emittances, you accelerate in a Linux, and then you return the beam with the phase shift of pi in RF length, so that you return the beam at the decelerating phase, and you take the energy back out of the beam. So you send the beam into a Linux, you return it, and you decelerate in the Linux, so you conserve energy. It's like a perpetuum mobile. You take the energy back out to have the energy available to accelerate the next.
So it's a Linux with the benefit of recycling that like finger time.
It's a Linux with recycled energy, and the reason you need that is that the currents in Linux are limited by the power you can supply, because the power is always beam current times energy. You have fixed energy, so your current is limited by the power you can supply. Rings have much more beam power than Linux, because there you can just recycle the beam all the time, right? So if you want to have the quality of a Linux beam, but with currents of a ring beam, you need to recycle the energy. Yes.
Yeah, I was wondering, what was the accelerator at Fermilab that uses the Pelletron pantograph?
So there's a recycler. Do you know the recycler? Yeah. So the recycler was built for antiprotons, because when Fermilab still had a proton-antiproton collider program, they need antiprotons. Antiprotons are so expensive to produce, so after you ran for a few hours with antiprotons, you don't want to throw them away. So they got decelerated, put into the recycler. In the recycler, you need to shrink the beam. So during the colliding time, the beam gets wider. So you put the antiprotons back into this recycler ring, and you need to shrink the beam back down so it can be used for the next collision program. And the shrinking down is done by an electron beam. The electron beam is produced by a pelleton.
Awesome, thank you.
Maybe a similar question in some regards, but all of these different technologies have the tron suffix. Do you know where that comes from?
Very good question. If anyone finds it out, send me an email. That is a very good question. Tron. Betatron. It must have started with a Betatron. It's the oldest one that has the Tron. Very good question. Yes.
Do you have a favorite accelerator type?
So I love C beta. I love energy recovery Linux, because that was a big part of my research programs. Plus, I think in the long run, particle accelerators eat up so much energy. One has to focus on sustainability. Otherwise, you cannot increase energy in currents and accelerators. And ERLs, energy recovery Linux, have been super breeding into sustainability. I mean, so that's my favorite for these reasons. The cutest accelerator, I think, is probably Betatron, because it's just like a ball play.
Tron is instrument. Green.
Tron is instrument. Okay. Any other questions? Okay, good. I hope it was useful. Thank you.